All right, so I'm going to talk about how to find the equivalent resistance in various circuits. So I'm going to go through a bunch of examples, and then we'll start to see some patterns that come into play. And I'm going to give you a strategy for doing this. So right now we're going to find Req for a circuit, the equivalent resistance. All right, and I'm going to start. I'm going to give you a nice simple series circuit. We've already done these before. All right, here's 3 resistors in series. We'll call this one 5 ohms. We'll call this one 6 ohms, and we'll call this one 2 ohms. All right, so if I'm finding the equivalent resistance, hopefully you recognize that that's in series. But I want to show you a way we can do this to reorganize. So I always like to go from the positive and draw an arrow to indicate how that charge would have to pass through the wire. And if there's only one loop, well, then it's in series. Right? And so there's no splits. And so I can effectively redraw this circuit by identifying the positive end and then move it along that pathway. And every time I hit a resistor, I'm going to draw it. And I can just redraw this circuit just like this, from positive to negative. And I can write in the values 5, 6, and 2. And now I can clearly see there's one pathway through. And so I can just add, right? Equivalent resistance is just going to be 5 plus 6 plus 2, and I get 13 ohms. So this is a method of redrawing a circuit to organize and identify what pathways you have. All right, so let's take it a step further now and add a more complex circuit. All right, so circuit 2 now is going to be a series parallel combo, and you'll see one of these in your WebAssigns. And so this is going to be helpful for breaking that down. So we have one resistor here, and then I'm going to draw these dots is where we get a split. So we split and we go that way, and we split and go this way. And these come back together here and go back to our supply. And this is 2 ohms. We'll call this one 6 ohms, and we'll call this one 18 ohms. So I want to break through and go and identify how we would set this one up. So hopefully you recognize that if I leave the positive, I can go through this resistor, I can take a right turn, and there's one loop. Or I can go through that resistor, I can stay straight at that split, pass through that resistor, and make your way through. Now keep in mind, you'll never go back through a resistor twice when you do these pathways. All right, so if I'm going to do a redraw, the first thing I'm going to do is identify those splits, and I'm just going to label this. This is a junction. I'm going to label that junction A, and the other point we have, we'll call that junction B. And that's going to be helpful here when we're redrawing our circuit. And so what I'm going to do is I'm going to start at the positive end, and I'm going to make my way to junction A. And before I get to junction A, I have to pass through that 2 ohm resistor. All right, so there's 2 ohms. But at A, I get a split. Right? A goes one way here and one way there. So I'm going to identify that like this. And let's take the high road. Well, that's going to go through the 18 ohm resistor. And the low road is going to go through the 6 ohm resistor. And those two pathways come back together at node B. And then node B makes its way back to the negative end. Right? So I've identified node A and node B, and now you see when I've redrawn this circuit, it's really easy to see that I have one that I have to pass through, and then I have 2 that are in parallel, right? And they visibly look parallel in this circuit. And so when I'm calculating my Req, I can now write my equation as 2 plus the parallel combo of 18 and 6. And when I calculate that, that's going to be 18 to the negative 1 plus 6 to the negative 1, that whole thing to the negative 1. And then I can type that in my calculator, and I end up getting a value of 6.5. So that parallel combo right here, if I do that in my calculator, I should get 4.5 ohms. And if I add that to 2, I get 6.5 ohms. So my equivalent resistance of this circuit overall is 6.5 ohms. Hopefully that makes a little bit of sense. Let's add a little bit more complexity here. All right, so I'm going to give you another circuit, and we're going to break this one down. All right, so this circuit, Again, just going to continue to move through and add complexity, give you different examples for drawing it. All right. Somebody needs to mute their mic here. Here's somebody coming into the room. All right, so this one I'm going to come through. I'm going to get here and I'm going to split. I'm going to go through a 3 ohm resistor. I'm going to go down through a 5 ohm resistor. From this split, I'm also going to go right here through, sorry, it wasn't a great resistor. That's an 8. We're going to merge back together here. And we're going to go through a 2 ohm resistor. All right, so we've got a little more complex circuit here, and I'm going to do a quick redraw so we can calculate it. All right, so we've got, let's start at the positive here. All right, and I'm going to get to this point. I have a split. Let's call that node A. So here's my positive end. I don't go through a resistor. I go right to node A. And what happens at A? Well, A splits. There's a high road and a low road. So I'm going to show that split here. And now I'm going the high road and a low road. Let's go the high road. High road goes through the 3, through a 5, and to another node. So I'm going to do 3, 5, and let's call this B. And so I'm going to go to a node here and call that B. If I take the low road from A, I pass through an 8 ohm resistor, and I go to B. So now I'm connected again. And from B, I go through the 2 ohm and back to my end. And so I've redrawn my circuit like this. And hopefully, you can then write it all together. 3 and a 5, this combo right here should be 8 ohms, huh? 5 plus 3 is 8. Right? And so now I can do this whole combo. This is one big parallel of an 8 and an 8. 8 to the negative 1 plus 8 to the negative 1, all to the negative 1. Well, that should give you 4 ohms. And then I'm just going to add that last 2 ohm resistor, and I get an equivalent resistance of 6 ohms for that circuit. All right, by breaking it down. So you can kind of take each individual branch and apply your series and parallel rules to it. Let's keep rolling here. All right, I think I have one more set here. So I'm going to show you a couple other patterns you're going to see. So 3 is probably as complex as we'll get in this class. We can go more complex, but I'm going to show you some different rules that end up, some patterns you might see that'll help you kind of do some mental math. So let's look at some basic patterns. All right, let's draw a quick circuit here in parallel. All right, let's say that's 10 and 10. Well, it turns out that if I type that in and calculate it, well, there's 2 in parallel, so you end up just dividing it in half. This ends up becoming 5 ohms. All right, if I do 4 and 4 in parallel, well, there's 2 of the same thing in parallel, and I'm going to get a 2 ohm. It kind of cuts it in half. Well, what if I have 3 branches? If I have 3 branches, and they all happen to be the same resistance, let's say it's 9, 9, and 9, it ends up being the same as 9 over 3. We get a 3 ohm resistance. Again, if I take my calculator out and I do 9 to the negative 1 plus 9 to the negative 1 plus 9, well, isn't that 1/9 plus 1/9 plus 1/9? 3/9, right? Which is 1/3. And if I take the inverse of 1/3, I get 3. So you see mathematically how that plays out using that equation. If I do a 4 branch of the same thing, if I have 4 parallel branches and they all have the same resistor, 20, 20, 20, and 20. I'd have 1/20th plus 1/20th, so I get 4/20ths, which is 1/5, and you flip it. And so it's really just taking 20 over 4, and you get 5 ohms. All right, so hopefully you see this pattern that occurs when you have multiple of the same resistor in parallel with itself. You can basically just divide that number by the number of times it's in parallel. Let's look at another pattern. In this pattern here, we have multiple resistors in parallel. Let's do a set of 3. And this is helpful for estimating. Let's say I have one that's 2, 50, and 150. If I were to calculate this, what do you think the equivalent resistance should be? And this is going to estimating. Well, a lot of guys are going to estimate some kind of big number because you got all these numbers in there, you know. But it turns out, if I were to calculate this, all right, I would have 1/2 plus 1/50th plus 1 over 150, the whole thing over 1, right? There's REQ. It turns out that that value is only 1.9 ohms. In parallel, the equivalent resistance, REQ, is always smaller than its smallest resistance. In parallel. Right? So just by looking at that, because I have 3 pathways that are in parallel, when I see 250 and 150, I look at the smallest one, and I know that my equivalent resistance better be smaller than that. So it's a nice little pattern that you would see. The last thing I want to show you is a series of things in parallel with the same type of resistance and see what happens. So let's do one like this. These are all going to be pathways. Here's a 12 and a 12. All right, let's do another with a 12 and a 36. We'll do another one here with a 12 and a 64. We'll do a big one, that same 12 ohm with a 1200 ohm resistor. And then we'll do one more here with a 12 and just a 4 ohm resistor. All right, so let's look at some of these things. It turns out 12 and a 12, we just learned about that, is going to be 6 ohm equivalent. Well, 12 and 36, right? Well, 12 and 12 is 6. 12 and 36 should be less than 12, but 36 is slower, so it ends up becoming 9 ohms when you calculate it. 12 and 64, well, it's got to be greater than 6 again, and 64 is pretty slow. You end up getting 10.1 ohms. What about 12 in a really slow pathway? Well, you end up getting 11.8 ohms. You guys see a pattern here? The bigger the resistor you pair with that 12, the closer the equivalent resistance will be to 12. If I did 12 and like 12 million, I'll probably have a resistance of like 11.9999999, right? But as long as that other resistance, the smallest I can get is going to be half. And so when I go 12 and 4, well, now 4 is my smaller resistor, so it's got to be less than 4, and it turns out this is 3 ohms. All right, so it's got to be less than the smallest one. So now we've seen a bunch of different patterns here with resistors. Hopefully, as you start to do these, you'll see how these things all play out.